Well, I have the great pleasure of introducing Tryphon Georgiou, who is a long-time both collaborator and friend. Okay? And now you know that Tryphon Georgiou is a distinguished professor at University of California at Irvine. And he has done some outstanding work during his career, which started in Minnesota, right? And he was sort of introduced together with Malcolm Smith, this gap metric, well, you were then got in the gap metric there, in robust control, that led to two Axelby outstanding paper awards. Now, you think that he has gotten two Axelby awards, but he actually has four. And that's I don't know if anybody here has had four Axelby awards other than Tryphon. Oh, Münzer-Rose. Oh, I see. But he's not here, right? So there is no competition here. There is no competition, okay? Now, what else can we say? Well, I'll tell also that Tryphon was a student of Rudy Kalman. And we have a connection there, although we didn't overlap, because I was Kalman's first postdoc in Florida. But you're a young man, so you came later, right? And then I got in a fight with Kalman, like many others. So I wanted to have revenge on Kalman. So I took one of his favorite problems, and I talked with Chris Burns about how we would solve this. We started to get good results, and then we realized after a while that Tryphon, in his thesis, had already done this. Some of it, yeah, at least some of it, right? So this is how really we started to work with Tryphon, and this has gone on till very late. We're still working on a paper, right?
Absolutely.
Oh, yeah. So now this is my introduction of Tryphon. Let me see. Did I make some notes? Is something? No, I won't say anything on the bad stuff. No. So therefore, this is my introduction of Tryphon, and he's a great man, great scientist, and everything like this. You know this by now. So Tryphon, what is the title of your talk now?
It's on thermodynamics, stochastic control.
Okay, I'll give the word to you now.
Thank you, Anders. Thank you, Anders, for the very warm introduction from the heart, as always. And thank you all for coming. It's absolutely a pleasure seeing you all. And I would like to thank the organizers for a superb conference. It's a distinct pleasure being here again in these grounds of KTH. I've been so many times before, and also seeing all these young people working and talking to all of you, a generation, more ideas and more creativity coming, and it's absolutely a pleasure. Now, for those younger in the audience, I was for many years at the University of Minnesota, almost 30 years, and I worked on different aspects of robust control, optimal control, estimation, filtering, and so forth. And a closely guarded secret of an academic is that we grow, and our interests grow with us, and we always have this freedom of exploring new things. So for the past 20 years, I've been enamored with stochastic control and shifted over different areas. And what I would like to talk to you about is sort of the marriage between stochastic control and thermodynamics. This is, of course, nothing new. Some of the giants in our field, Jan Willems, Roger Brockett, Sanjay Mitter worked on this. And I only wish that they were around and in the audience. So it's a great pleasure being here and discussing recent developments. The subject has taken quite a bit of advances in recent years, and there is a significant following within the physics community. It basically brings together statistical mechanics, stochastic control, and non-equilibrium thermodynamics. That's the title of the talk. And the subtitle highlights the fact that right now with stochastic control, we can address some hitherto untouched problems who have been sort of puzzling the community for a long time, working very far from equilibrium and talking about quantifying the power that an engine, albeit simple mathematical models of engines, can generate. Before I move on, I want to say that this has been mostly of what I will tell you is joint work with a number of bright students and postdocs that I've had, Olga, Amir, Rui, Yongxin, and Jordi in recent years. So our story begins almost 200 years ago at the dawn of the Industrial Revolution. The first picture over there is Sadi Carnot, a very young, brilliant engineer. His father was also an engineer. He wrote a monograph, and I'm sure most of you know, and he is the father of thermodynamics. Almost at the back of an envelope, he conceives the quasi-static concept of quasi-static transitions for thermodynamic systems and comes out with Carnot efficiency, how efficient a thermodynamic engine can be, which alternates contact with two heat baths. The second person in the middle among the two of them is Gaspard Monge, the father of optimal mass transport, among other things, a great mathematician, founder of École Polytechnique, and we'll be talking a little bit about optimal transport because this gives us the tools to describe and quantify transition thermodynamic systems far from equilibrium, where now the thermodynamic state is not a point in a finite-dimensional manifold, but a probability distribution. The probability distribution is metrized based on work that goes back to the 1700s in Gaspard Monge's work. And I'll tell you a few things in the next few slides. And the last one is Boltzmann. So, and there are many other more giants that brought all of these things together, entropy, optimal transport, and thermodynamics. The paradigm, I'm going through this, I would like for you to keep in mind that the new tools that we have, and stochastic control in particular, which is not much different from all of this, allows you to think of systems going from the Newton paradigm, we have a finite position, velocity, and so forth, to laws governing collections of particles. And thermodynamic states are going to be probability distributions. So there are a number of interlinked themes, and I'm not going to stay very much on this slide. Optimal transport relates very closely to work and dissipation of thermodynamic systems. I'll highlight this. The work there starts 200 years ago in mathematics with Gaspard Monge, Leonid Kantorovich, he got the Nobel Prize for related work. And then stochastic control figures very prominently in all this. And Schrödinger is another name, but I'm not going to mention very much about him. Then, of course, in physics, statistical mechanics, from steam engines all the way to concepts of computation will enter in the picture. And then in the last few decades, people have tried to use tools and concepts of that to analyze engines for biological and nano engines systems. I will go through a number of ideas, but the high point will be the last part of the talk, where I will explain how anisotropy enables energy conversion and how we can quantify limits to how much can be achieved. So in the next 3 slides, I'm going to give you a bare bones exposition what optimal mass transport is. And the only reason is to understand and basically explain that thermodynamic states are distributions, and we need a metric to quantify distance between distributions and path between distributions. So the problem of optimal transport was conceived by Gaspard Monge when he was working as an engineer in Napoleon's army, and he wanted to move mass from one point to another to level the roads and move the cannons over. So the cost he wanted to minimize the cost, and now this is not exactly the type of cost that he wanted to minimize, But in the incarnation that we're going to see and are concerned, you have a quadratic cost. T is a transportation map, and you want to move mass from x to y, and the mass is d mu. And you want to do this with minimum transportation cost. That, when you solve this optimization problem, the distance between the two measures, two distributions mu and nu, is called the Wasserstein distance. Now, this problem has a long history. It was a very technically difficult problem. Many great mathematicians, Abel, for example, worked on it. It's highly nonlinear in T, and he had to wait for 150 years before Leonid Kantorovich regularized this problem and devised duality theory to solve it. So this is all sort of bare bones, very quick. So Kantorovich's idea was, instead of looking for a transportation map, you look from a joint distribution that has specified marginals. So this is highlighted in the picture over there. Instead of looking for transporting, you look at the joint distribution, and you find the joint distribution which minimizes the transportation cost from x to y. That simplified many problems that, because mass can split from one location to many, makes the problem simpler. And when the two marginals are absolute continuous with a Lebesgue measure, what you get is that the joint sits on a very fine set, thin set, which is the transportation map. So all of that brings us to about 1990. And Leonid Kantorovich got the Nobel Prize because transport has uses in economics, transportation of resources, and many other things. And then we have a brilliant discovery by Benamou and Brenier and many others, where the same distance can be written in a slightly more complicated way as an action integral. So if you have 2 points in Euclidean space and you would like to minimize, you look at the quadratic of the Euclidean distance between them, this cost is also the same as the integral square of the velocity from beginning to end over all paths. Because the optimal path is you go in a straight line with constant velocity. That extremely trivial back of the envelope computation, which is high school level, gives rise to this beautiful formula that the Wasserstein distance between densities ρ0 and ρ1 is the infimum over rho's, densities, and velocities along a path that steers, this v over here should have been u here. V and u are more or less the same. U is control and v is velocity. So it's okay. So you have over here the integral of rho v squared, which is basically kinetic energy. And the 0 to 1 integral is the time it takes you to go from beginning to the end. So this is action integral in the style of physics. And it turns out that this gives you a Riemannian structure in the space on the space of distributions, where you identify the tangent directions with velocity fields. So this is quite deep and technical, but this is the only thing that you need to remember, that the Wasserstein is average kinetic energy. This is action integral, and in fact, this is a Riemannian geodesic distance with the Riemannian metric being encapsulated in the integral here in the middle. So now let's go a little bit fast forward, and we're going to move now into the subject matter of the talk, stochastic thermodynamics. Again, the way we conceived thermodynamic systems, our thermodynamic state is a distribution. And now, what is this new discipline? This allows you to study thermodynamic systems at the level of individual particle, and then a collective of particles. You have average quantities, which is entropy, work production, and so on and so forth. And allows you to study systems very far from equilibrium. Applications include biomolecular machine, transcription mechanisms, and so on and so forth, and exchange of energy at the kBT energy level. Kb is the Boltzmann constant, and T is the absolute temperature. So there are still enduring questions, and we're pecking on the subject on the sides, and we have the theories developing very rapidly. The picture that you see on the right, I'm going to make a few comments at the very end, represents a bacterial flagellum, which is a remarkable engine. It's basically a flagellum which rotates at 2,000 RPM, maybe more. Bacteria propagate at 17 body lengths per minute in suitable environments. Can you imagine Mark Spitz going 17 body lengths per second? And exactly how these engines work has been the subject of extensive studies. So more and more we get insights into the ability of these engines to work and transcribe different forms of energy to mechanical energy. So now let's go down to the basic model. This all goes back basically to Einstein and the conception of Brownian diffusion, Brownian particles. So the way to think about this, you have a Brownian particle which is bombarded by smaller particles. So it's a particle that sits inside a heat bath. The average kinetic energy of the particles bombarding is the heat of the medium. So then, again, this goes back to Einstein, and you can understand a lot of things going back to his paper 1905. This is the famous formula where the drift current due to diffusion balances out current due to forces. So if you tie a string to a particle and you try to pull it, the head wing from the bombarding particles on one end balances against, gives you the force. And the diffusion also links through this famous formula. So when all of this is put together, you bring back Newtonian intuition, and you have the underdamped Langevin equation, where position is the integral of the velocity. That's the first equation. And the second is acceleration is due to a potential, which you can think of it as control. There is some friction, and there is the thermal excitation. The thermal excitation is, the dB is Brownian motion. The T is the temperature and can be time varying. And the 2 gamma kBT, these are all formulas that go back to the foundations of the subject and explanations that go back to Einstein's contributions. So that's the underdamped Langevin equation. Quite often when you have particles inside a colloidal, you have colloidal particles, and you make the assumption that the time scales allow you to make the simplification that you have overdamped dynamics, and this is what we're going to do in this talk. You can also do this with inertial forces. So when inertial effects are negligible and the time constant of observation is much larger than the ratio of mass over the coefficient of gamma, then the previous equation simplifying, you have dx is equal to the gradient of a potential, which you can think of as your control, and then you have stochastic excitation. So this is where we begin. So the first equation, the overdamped Langevin equation, is simply the dynamics of an individual particle. This square root 2 gamma kBT is not so important. The important is this diffusion coefficient is time varying. It can be time varying. Then the Fokker-Planck equation is written below. And the Fokker-Planck equation can be written as a continuity equation, where the Laplacian can be brought into a term together with a potential and written in this form. And written in this form as a continuity. So it's the divergence of rho times v. And the v here includes the gradient of the potential, as well as a gradient that has to do with the thermodynamic, the density. So now at the level of, oops, let me just, so at the level of the individual particle, you have that the energy of a single particle can be split in this way, where the first term, the partial with respect to T of the potential, can be identified with work, is the way that the particle interacts with a potential. The second, which is a Stratonowicz differential, can be interpreted as interaction with the heat bath and heat flowing from the particle to the heat bath and vice versa. So on the left-hand side, the expressions which are W, Q, and are those two terms for individual particles, and when you sum them, it represents the energy of the particle, internal energy. Now, if you take expectations, then this is at the level of the ensemble, and the expression here basically represents the first law of thermodynamics, that energy is conserved. Now, the expression to the left is now we are going to discuss the second law of thermodynamics. The expression to the left is the entropy of the ensemble, which is the expected value of the logarithm of rho. The logarithm of rho could be thought of as the entropy of an individual particle that sits within some density. In other words, the way you describe it as a member of some ensemble, it can be the information content of that can be thought as log rho, and the expected value of that is the average entropy over all the particles, and this is the usual expression of the Shannon entropy. The free energy here on the right, which intuitively is the energy that you will be able, under some conditions of temperature, you can extract from the ensemble, is the internal energy, E, minus kBT S. And this you can also write it as a relative entropy of the current state of the thermodynamic systems relative to the stationary distribution. So this slide contains quite a bit. Now, if you take the derivative of free energy, you have it in this form, where there's a first term here, which, if you trace it to the previous slide, is the derivative of the work, and then there's another term here which is negative, and this is expected value of V squared. That ties the whole thing to optimal mass transport. This is the integral rho V squared, the thing that we saw earlier. And this is negative no matter what happens. This represents dissipation. So integrating over time, if you go from one state to another, the work that you're putting in is the difference of the free energies plus this expression, which is dissipation, and adds up no matter what you do. And this gives you an expression for the second law that the work you're putting in is greater than the change in the free energy. But this gives you a bit more, because it tells you exactly, if you have a finite time transition, how much dissipation you're going to incur. So the expression is that the average work is the change in the free energy plus 1 over the duration, if you trace all the formulas, times the Wasserstein length of the curve. Which curve? The curve is a curve in the Wasserstein space. Points are densities, and you move from one to another. So, for example, schematically over here, what you see is you have a bimodal distribution that steers into a unimodal by changing the potential. And in the process, you are going to have to provide some work. This ties to some absolutely foundational work in the 70s of Landauer, where the question was, what is the minimum amount of information, the work that you need in order to perform some computation? What is the cost of carrying out computations? And the consensus right now is that the cost is in bit erasure. And the cost is in erasing the content of a bit, and basically changing a bimodal to a unimodal by suitably adjusting the potential. The schematic over here highlights this, that you can have either a 0 or a 1, and then by changing the potential, the particle moves to the ground state on one side of this bimodal, the two-well potential, erasing the memory of the past. So you're going to see this kind of conceptualization of steering distributions by changing the potential, which is very analogous to opening and closing the pistons of a cylinder that has molecules under some sort of temperature. So exactly this conceptualization that you have a distribution, so what you see in grayscale is a row, a distribution, a density of particles sitting inside a potential. So these are all quadratic potentials, and we're going to be doing this for Gaussian excitation and quadratic potentials. So what you see there, this is a model of a Carnot engine. So you have a distribution sitting nicely inside some potential, and then you open up the potential, you relax the sort of the spring constant, the distribution opens up, producing work, very much like when you retreat a piston of a cylinder that is heated. And then you change the potential suddenly. This is an adiabatic transition vertically. Then you bring the ensemble in contact with a cold temperature. This is over here, Tc. This represents hot temperature. This is cold. And then now it's less costly to close in the potential and bring it back to the original state. And in this way, you create a model for a Carnot cycle. The advantage of using this type of models is that now you can carry out these computations on the budget of how much energy was produced and how much energy was exchanged with the environment. So I'm going a little bit fast on this, but it's relatively straightforward. So in this part of the cycle, one, you get work out. There is no exchange of work here, and then you put work in. So when you go through the cycle and you integrate, you have the work that you get, and the portion over there which has to do with dissipation are the irreversible losses. And you can work this through, and you can get expressions which extend the classical work on efficiency of a thermodynamic engine, but give you quite a bit more. So the expression on efficiency that you get is the TH minus TC, the high temperature minus the low temperature, divided by TH. This is the change of the entropy between the endpoint states. But you get a couple of terms here that degrade the efficiency, and this have to do with the Wasserstein distance between the two endpoint distributions. And this is the period of the cycle. So in the limit, when you have a quasi-static transition, you recover Carnot efficiency, which is here. But now you also have the possibility, because you're going to be doing this in finite time, to ask the question, how much power am I going to get? And the expression for the power is like this. So now you can explore this for different situations, and you can fix the temperatures, or you can have a time-varying profile and ask questions: how do you optimize the potential, the starting point, the ending point? And there has been a lot of work on this in the last few years. When you do quadratic potentials and Gaussian excitation, you get very, very simple formulas that seem to be the extreme of what can be achieved. Now, I want to leave this in the background. So now, biological engines and engines in the real world don't work this way. We don't have two heat baths that we bring the ensemble in contact with one and then the other. What happens is you have anisotropy. The reason there is life on Earth is because we have this 6,000 Kelvin photons coming from the sun that we emit back in space as 300 Kelvin photons. So there is a gradient, and inside this gradient there is basically a mechanism that transduces energy from one heat bath to the other, and in the process you get some work out. So this is what I would like to explain to you. how you harvest energy from anisotropy, which is basically how nature does it. So this is a very, very simple model. It's called the Brownian gyrator. So what you have over here, and we are going to see very large-scale engines working in this way. What you see over here is you have a 2 degree of freedom. We're going to see this shortly, stochastic model. You have voltages over here and charges in the capacitors. This is driven by 2 Nyquist-Johnson resistors. So these are 2 resistors in different temperature that provide stochastic excitation. So you think that this is going to reach some sort of a stationary distribution, and it does, but it's not equilibrium. So if you look at the voltages, voltage 1 versus voltage 2, you get some nice Gaussian distribution, but the trajectories, you create a curl. There is a circulation. So it's not equilibrium, it's stationary, but not equilibrium. You can think of it as sort of like a mass connected with 2 strings that are jiggled. And then if you see on average, this is going to be going around a circular motion. And this is the type of things that you try to take advantage of and extract work out of it. And you're going to see how this is happening. So this is a model for that. You have 2 degrees of freedom. That's the key. You have different stochastic excitations. One is the hot heat bath, the other is the cold heat bath. And the particle circulates in there. You have a control parameter, which is describes the potential. And then you look at the formulas that we had before, and you try to express work exchange with the external work and with the heat baths. So what you have over here is, now this becomes very much like control theory. So the stochastic, the state of the stochastic system is a Gaussian distribution described by a covariance function, covariance matrix. So sigma is a covariance matrix centered at the origin. And it's steered by altering the matrix K, and here you have a Lyapunov equation. So that's your control. And the stochastic excitation has to do with this temperature matrix, which is diagonal. You specify control action now. You can specify as a function of sigma and sigma dot, and you can steer the thermodynamic state on the thermodynamic manifold and do the energy budget. I'm going to simplify these expressions by replacing the K as a function of sigma and sigma dot. You don't need to know what the control is. You can always compute it if you know what path you're going to follow. So by doing that, the only parameter we have to worry about is sigma. Sigma is just a covariance. And we simplify it even further. For simplicity, we can take the determinant of sigma to be constant, and this is some characteristic length. And the sigma has some eigenvalues, and the ratio of these 2 eigenvalues is important. We're calling it R. And there is here a unitary matrix that brings it into a diagonal form that is rotation by some angle theta. So those 2 things describe a covariance matrix, a 2 by 2 covariance matrix by a point in polar coordinates. So if I give you in polar coordinates Euclidean space a point, you have to view this as a covariance, and you have to think behind that sits a Gaussian, nice Gaussian distribution. And what we're going to be doing is we're going to be moving in this Euclidean picture in polar coordinates, and each point represents a distribution in the Wasserstein manifold. So the thermodynamic cycle now is going to be sort of a path. Here is the origin. The origin means R is 0. R was the ratio of the eigenvalues. So the Gaussian distribution is completely symmetric, and you see here a circle signifying that. So this is the level set corresponding to a Gaussian distribution with equal variance in all directions. Now, if you compress one of the axes, then you squash the Gaussian distribution, then you can turn it around, and then you squash it back, and that represents a thermodynamic cycle. So now we can do the budget, energy budget. So the thermodynamic state, again, is described by this covariance. And the K it doesn't worry us, because if we know what the thermodynamic state, the path is, we can compute the K. That's the internal energy, expected value of the kx squared, which is the trace of k times sigma. You take the derivatives, and then you have dq and dw. And if you write the exchange with the heat bath, you see that there are two terms. One of them is linear in sigma dot, and the other is quadratic. Quadratic means that if you go infinitely slowly, this disappears. It's completely squashed by the first term. So this is the quasi-static exchange of heat with the environment, and this represents dissipation. The second term is precisely relates to the Wasserstein distance as you're moving in the thermodynamic manifold. So I think I have few minutes, so I have to move a little bit fast. I have quite a bit. So, sorry, this interruption kind of slowed me down. So when you do this energetics, you see that the quasi-static work can be written, this is can be written as an area integral, and the expression here has to do with the difference between the temperature of the 2 degrees of freedom. Then the dissipation can be expressed as a length, and this is exactly the Wasserstein length. And you are looking now for thermodynamic cycles in this. Pictorially, every point is a distribution, and any path here, any closed path, is a thermodynamic cycle. The area represents work that you get out, and the circumference represents dissipation. So maximizing efficiency or power becomes an isoperimetric problem. And this is probably the most important slide, which tells you that there is an area integral, there is L, which is a Wasserstein length of the cycle, and these are maximizing cycles that tell you how you're going to squash and open up the ensemble by allowing the potential to change, to maximize power or efficiency. And we can write, for example, that the workout over a cycle is the area minus mu is some physical parameter written here, and L squared is the Wasserstein length of the perimeter. So this is absolutely a new advance in how we understand the efficiency of these engines. Now you can say, well, that's all good and fine, but what does it actually mean? So what I will show you, so this is also the expression about efficiency, and you can find out that the maximal efficiency can be expressed in a certain way in terms of some physical parameter. So the size of the isoperimetric curves has to do with the time you allocate to go through the cycle. If you try to go too fast, then you go off the top here, and the dissipation exceeds the amount of work you're going to get out. So now, let me show you a little bit of how physically you can understand this. So going back to the Brownian gyrator, you have nicely over here 2 heat baths, and you have some sort of a circulation of current where heat flows from one heat bath to the other by way of the electrical degrees of freedom. The fluctuations there allow energy to be transferred if you don't do anything. Now, how am I going to get work out of it? To get work out of it, I have to change the capacitances in a time-varying fashion. And conceptually, you can do that quite easily by having the electric material pads that are being sucked in or pushed out depending on the voltages between the different capacitors. If you do this, at least theoretically and cleverly, you can create a torque that can rotate a load in the middle, and you can bring the whole contraption into a limit cycle oscillation, which allows you to tap onto some of the heat that goes through the electrical degrees of freedom from one heat bath to the other, and transduce this into mechanical energy. So this slide here encapsulates that. I think I have a little bit more than we can go slow through this. So this again describes phase plane and limit cycle oscillations. So effectively what happens here is you have it almost like you have a pendulum that due to the imbalance, the anisotropy, there is a constant torque applied to it. So if you let it be, it's going to settle there. But if you move it, it will start rotating, because the torque will produce more energy over part of the cycle. And this is very similar to the Stirling engine. This is a large-scale engine where you have a cold and a hot. You can buy a Stirling engine for $90 from Amazon, put it on your coffee cup, and it will start rotating. So, and it's exactly this, that you generate basically the anisotropy creates a tilt to some quadratic potential that can drive the engine. You can put many of those engines in parallel, and you can generate motion without requiring any tipping at the beginning, because sometimes the Stirling engine you have to push it a little bit. And there are reasons to believe that there are analogies to flagellar motors, which if you look at it, the flagellar motor has some membranes, and there is an ion gradient that is maintained between those two, and ion currents flow through the contraption with proteins, generating torques. And if you look at it, it looks almost like a 6 or 12 cylinder engine. So there are pieces of that generate torque, and the flagellum works so efficiently. So, so this kind of wraps up a little bit the story I wanted to share with you, that we have now the tools and the conceptualizations and the theory of stochastic control that allows us to study such systems. And the coordinate space gives way to the Wasserstein space. We think of the thermodynamic state not as a point in a finite-dimensional manifold. We don't have any more quasi-static transitions. Then Newton's equations become Liouville equations, and the story continues. Right now, what we have is, at least for the simplified models, this answer to the hitherto unstudied question of how much power you can generate. And it's very satisfying that this relates to geometry and an isoperimetric problem. And I would like to close with this picture here from Gaspar Monge's memoir from 1781, where he was trying to move mass around. And to say that it's quite interesting one would have liked to see his reaction when this concept of Wasserstein space, Wasserstein distances, which is basically out of his work, have reached so many fields, from machine learning, computer science, thermodynamics, optimal transport, uncertainty, control of uncertainty, and many other fields that are rapidly expanding in the last 20 years. And with that, I close. This is the team, and this is a member of our team drawing inspiration from nature. Thank you very much.
Well, thank you. Thank you, Tryphon. Do we have any questions for Tryphon?
John.
Oh, there, John.
So thank you for a beautiful talk. The question I have to ask you is this. You keep moving from physics to information and back. And this has to be done with great care. If I go back to the back pages of the fundamental book of Lincoln Way, Carver Mead, there's a little appendix that shows why entropy comes into the picture, even from computing. And it has to do with how much you can close various elements, and this translates to heat and so on and so forth. And that is a very simple way to describe why Jane later on said, you know, we have entropy in physics and entropy. Okay. But now when you go to these fields, all right, and you move from mechanics of moving grounds and then go to moving probability distributions, the physics may be different. Especially when you, this is beautiful for what you did, but most of the physics you used here are classical physics.
Absolutely, yes.
So if I go to biology, for instance, and if I go to other places where there's chemistry and there's macro interactions, you get into other phenomena that may change the picture completely. So the question is, where are you going in that path?
Your point is well taken. This is a very simplified model. And this is sort of like almost like a simple paradigm.
So that's beautiful. It's just
yes.
When you put new physics, what happens?
When we don't know that yet. The models are going to be insufficient. These models will be insufficient when you start talking about biology. Absolutely.
Or you go to quantum noise and quantum
oh yes, absolutely. Quantum noise and all other things. But this is just highlights.
You think there will be analogs of that?
I think so. I think there will be analog to that. And the story is out there for you to explore. I mean, everyone.
We have already quantum information theory.
Mm-hmm.
We have many of them.
John, thank you very much. Your point is well taken. I cannot answer it because the answer is not here yet.
No, but the question is, are you going to go that way?
Yes,
Okay.
actually, yes.
I have to stop this because the next session starts in 20 seconds.
Oh, thank you very much.